The following is our in-depth final video prior to install of the Autolance system. First, we have our laser safety devices installed. Our E-Track houses an electrical cable for the solenoid valve, along with an air line, and an air line for the dispense head and the fluid line. That fluid line is connected to the PCF system, which is fed by a 47-to-1 supply pump. Our inbound air connection starts with a filter regulator unit, then goes to a two-stage filtration unit with an automatic float drain. This is a separate air regulator specifically for the dispense head. Our PLC controlled air solenoid bank. The supply pump air inlet has a pilot valve so we can control it from the PLC. With the new carbon fiber lance, we had to add a rolling mechanism at the front half of the carriage. This eliminated the need to have rollers down the length of the lance, reducing weight. This is our solenoid valve that is actuating the dispense valve. It has an open and close output, resulting in a great response time. Ball valves on the inlet and outlet of the dispense valve for quick changeout. In this clip, we have a close-up of the roller system while the system is running. We realized after going with the rolling system that we could quickly make adjustments on the height of the roller to combat the deflection. So we've got this system up front that is fully adjustable so we can make quick changes to try to help with deflection. While the lance extends out, the PLC initiates a deflection routine that raises the last actuator by 1 millimeter in 4 increments as the lance is extending out, to try to eliminate as much of the deflection as possible. And if you look closely, you can see that. On this portion of the video, we'll go through the HMI screen of what the operator will do through a typical job run. We will first select the pipe diameter size, and then below that we move left from right. We start with enable the motors, we reset any error codes, we hit the return to home button, and then we drive to location. On the project start screen, it is the same order of operations. We start with enable the motors, reset the error codes, return to home, and then start the project. The return to home button retracts the actuators all the way back until it stops. This allows it to know its absolute position in space. Now we are going to show the fluid control system, Graco PCF, run through a cycle. You can see the style and flow command change as someone is changing the HMI screen for the different pipe diameters. On this simulation, we're going to use 8-inch diameter pipe. And if you refer back to the Excel document that I sent out, y'all said that it needed 1.67 gallons on the finished product. So that is a total of 6,322 cc's. So if you look at our target there, that's where we're getting that from. So on that Excel sheet as well, it shows that we need a flow rate to achieve that of 3,422 cc's per minute to achieve that 1.67 gallons. So as we go through this video at the very end, take note of what is actually requested to what the target is. I have written a backdoor in the HMI screen so that we can change the flow rates per pipe diameter. So if we determine that these numbers that were originally given to me are not enough or too much, we can make these changes just in the HMI screen. This is our laser measuring device that will be on the other side of the pipe that will allow us to know when to turn the trigger off and back on. This is a remote start project or stop for the operator. We just need to know where we need to put this on the carriage. Just a quick overview of the PLC program that we're running on this system. But something to note is that we're just calling for recipes. So the recipes are actually set up in the individual devices. So there is the 4-axis controller, so all of the step data is actually in there. It's not in the PLC. And all the lance, speed, distances, all that stuff is handled through its controller. And then the PCF is handling itself as well. So we're just sending one global recipe out to change all the parameters per pipe diameter. Here I just wanted to show how much memory we are currently using for this project in the PLC, just to show that we have plenty of room for growth for future projects. This is the Festo configuration tool. It's a free software that we can give you guys, but it is storing all the information as far as speeds and distance. So this is what the PLC calls for when we say 6-inch diameter or 8-inch diameter. It's changing the recipe numbers to call for these different steps within this controller. You can also use this software to manually move the lance actuator if needed. Now this is the SMC 4-axis controller software. This is another free software that we can give you guys. This will give you live tracking data, and it also has all the step data as well. So when we change the pipe diameter, it's calling for these different recipes that are in this software, so we can actually change the speed at which they're lifting and the distance or where they're traveling to. The reason for this quick overview was just to show that with this free open source software and the way that it was programmed, that you guys could easily change the height of the lance, the speed of the lance, the distance, and actually the flow rates. So there's no real reason for a PLC programmer to be there to be able to make these changes if they come up. This is just a picture of the PLC enclosure as it is now. This is our final clip of the system running one cycle, where we can take a look at the deflection on the lance as it's fully extended out.